On behalf of the organizing committee and the National Center of Theoretical Science, NCTS, I would like to express my very warm welcome to all of you, especially those of you from abroad. I hope all of you will have a very fruitful week in Taiwan. Well, as you know, this meeting is intended to be one in a series of meetings on Amplitudes. Last year, the first meeting was held in Hong Kong by the IAS of Hong Kong University, and this year here. And next year, I'm not completely sure where it will be yet. I heard it will be in Zhejiang University.
Yeah, I think
in Beijing. In Beijing. So okay, in Beijing. Okay. So the most updated information will be in Beijing. So we hope that through this series of activity, Amplitude, the research in Amplitude will grow strongly and healthily in this region, and in particular in Taiwan. NCTS as a national platform is intended mission to promote excellency in research in theoretical physics, not just string, but everything in theoretical physics. We welcome international collaboration, and we hope if any of you are interested with ideas and comments, you are very welcome to discuss with me and or with one of the locals and develop the ideas. And apart from science, Taipei is a very interesting city. It is the place for some of the most famous museums in the world. For example, like the National Palace Museum. Also for some of the famous architecture and buildings like Taipei 101. So I hope we will have time to explore. And recently, in one of the British TV programs, I think it's the BBC, Taiwan is voted one of the best places in the world for food. Well, I don't know whether it's true or not, but certainly it's very good. Okay. So I hope you will also enjoy. And finally, I hope all of you will have a very productive, including myself, productive week in science here. Thank you. Visual comments to make.
we just started.
Okay. So okay, if there's no particular comment, so let's start the first lectures on this morning. So is on platform. So the first lecture will be on amplitudes from amplitude to form factors by Gang Yang.
It's a great pleasure to be able to come here. I'd like to thank you team for the invitation. Can you hear me? Or do I need I can speak louder. Can you hear me? Does everyone have the password? So the title of my lecture would be this functional method from amplitude to form factors. So because this is an opening lecture, I think also told me I need to introduce some basics of scattering amplitudes. So I think a major part of today's lecture will be tell you something very basics about scattering amplitudes. Hopefully this will be a warm-up, also set up some conventions and basic facts for the later talks. So, and another topic of this lecture would be the form factors. So, so we are interested in the interactions of particles, that's denoted by some this label phi, and some local operators. So the general form there will be n particles and n local operators. So if there's no operators at all, this will be scattering amplitudes. If there's only single operator, we'll call this particular form factors. And if there's no particles, no asymptotic states, this is would be pure correlation functions. So I think I have no, in particular for the audience here, I need not much need to emphasize why scattering amplitude is important. So it's one of the most fundamental observables that's associated to theory and the high energy physics. So it is by comparing theoretical prediction and experiments, we can understand how the nature works at the most fundamental level. So this is, of course, definitely very important. And on the other hand, if you open any quantum field theory books, there will be a lot of part also talking about operators. So this also plays a very important role in understanding any quantum field theory. And in the past, I think like 30 years, there have been remarkable progress that for development of these scattering amplitudes. There's many surprising simplicity and nice properties. So the part of the goal of this talk, lecture, I want to at least tell you something, how to transfer this knowledge to the understanding of more general class of observables, in particular those associated to these local operators. And the form factor would be a very important observable here to associate this on-shell part and in some sense this local operator off-shell part. Okay, so that's a part of the motivation of this lecture. Okay.
Of course, application of form factors is important, like electromagnetic and so on. But you are more concerned about mathematical structure of the form factors. Not the use of the form factors.
Basically, I'll introduce how to, based on amplitude techniques, how to these methods can be applied to complete form factors. So for particular application, I will mention some examples, but that's basically it will be talk about the mathematical structures of these form factors. Okay. So please do interrupt whenever you have some questions or comments. So first, about the amplitudes. So I should say there are some very nice lectures. L1 and meeting. Also, there's another one by Han and Lefker. This is a think these two references most are to date, updated to the status of this development amplitudes. Of course, there's also some other nice lectures, like alongside this very nice TESI lectures in 1996, and also you can find those as reference in these two lectures. Okay. So we are interested in the n-particle scattering. So this would be, let's label it 1, 2, 3 to a particle. And for the introduction part, we will focus on the gluon states. So this what is this function amplitude as a function of some physical property of these asymptotical states. And for gluons, each gluon has a momentum, and there is a spinor polarization vector. And there will be a color index. So mostly we will be focused on X4. Yang-Mills or super-Yang-Mills theory. So this is a theory of massless particles. So how do we consider this object? So a very conventional way that people can simplify this quantity is to extract some color factors. So let's write down this so-called color decomposition. So a given amplitude with those quantum numbers, it can be written as a single trace of these color factors. What are these trace? Let's consider a Feynman diagram. So each interaction vertex, for this trigonal vertex, is a color factor called ABC here. So this is given by this anti-symmetrizes this BC index, this single trace. So for any given Feynman diagrams, there will be color factor here, color factor here. So while you compute a full Feynman diagram, you make contraction of this color, this FABC, and you take the expanded product. So you will always obtain a single trace. So this is for tree amplitudes. There's no multi-trace. But for loop amplitudes, you would have multi-trace. So this is definitely not a single order, right? So when you do products, you will have a mix of different orders. How many orders you can have for this? So there's basically a sum of all permutations of this NT matrix. However, because it's traced, so it's cyclic invariance. So you have to mod this. So I have to sum over all non-cyclic permutations. So we can put a sigma here. So it is usually people, when you talk about amplitudes, people actually consider this so-called color stripped amplitudes. So this is object that we will from now on will be focused on this color stripped amplitudes. However, I should make a comment here. Actually, although normally people would infer for the tree amplitudes, this would be very interesting and it has nice properties. For example, because it's color ordered, it associates to some planar diagrams. And this you would have, in particular for this planar limit, you have very nice symmetry properties, like due to Wilson, Casper-like Wilson lines, Wilson loops. So this I will not, hopefully some other speakers will talk about this. But even in this picture, we have factorized the color factor. In many other pictures, the color factor plays a very important role. For example, this so-called color kinetic dualities developed by Zwiebel, Rasko, and Johansen. So these color factors combined together with kinematic factors play an extremely important role here. But we will not talk about that in this lecture. So now we are focused on this amplitudes, which is a function of momentum and polarization vectors. So because it's massless, so next we will introduce this so-called spin helicity form. So we have massless momentums, which is satisfied this on-shell condition. And a nice trick in this case is one can always write a spinner, a vector, Lorentz vector, in terms of a bispinner. In this way, more explicitly, we introduce this sigma matrix, where this sigma mu is given by time component, is our identity matrix, plus this part matrix. So this is explicitly given by in terms of these four components. So if you consider the trace of this matrix, it is zero because of the on-shell condition of this massless momentum. So and just from pure mathematical fact, so given any 2x2 matrix which has zero determinant, it can always be written as because in this case either the row has to be proportional to each other or the column have to be proportional to each other. So you can always factorize it as two spinners. So this is a lambda, which only carries this alpha index, and this lambda tilde carry alpha dot index. If you like explicitly, this would be lambda alpha equals to 1, lambda tilde alpha equals to 1 dot, and so this is a lambda will be more fundamental variables that we will mostly use. So there's a property about this sigma matrix. So this will immediately give you, for any Lorentz product of two massless momentums, what do we obtain? Let's first introduce this notation here. Where this ij is defined by this contraction of the spinner index. So similarly for the Ji, angle bracket, and for the square bracket, it's defined in a slightly different way. So you see, the order here is IJJI. This is what mostly used in the QCD literature, and I think in most some, for example, the Wheaton's first using twister variables. In those literatures, actually most would be a sign difference. So this is just a side comment. If you look at the different literatures, you have to be careful about the conventions that they use. Okay. So any questions? Okay, so good. So when we write the form vector, this momentum in terms of two spinors, there are still extra degree freedoms. So, given any lambda and lambda tilde, one can make a scale transformation so that this could be the T lambda and T inverse lambda tilde. So you see the products don't change your momentum. So this extra degree freedom is also very important. This the scaling property is called the Ito rule. It's SO2 for your massless particles. So we assign this the lambda as a helicity, which is let's define this for each particle we can define independently. This is called a helicity operator. So lambda has a helicity minus half, and lambda tilde has helicity plus half. Okay. So having talked about the momentums, so how about the polarization vectors? So given in terms of spin helicity formalism, polarization vector has a very nice representation. So let's write down the answer. So consider the so we don't assign us helicity for the moment. Let's just write down two possibilities. I will explain the notations. So this C is an arbitrary spinor that we can choose, and lambda is a spinor associated to the momentums, this I particle. And there's a second way that we can introduce this lambda, and for this C tilde as an anti-holomorphic part. So let's come to the helicity of these two polarizing vectors. So there's lambda tilde on the numerator and another lambda in the denominator. So there's a plus half minus and minus half. So this is plus helicity. And this is, if we do the same counting, this will give you the minus helicity. So there's some numerical factors in this talk. I will not be careful about these I factors or numerical factors here. So can check, let's call this, because it is a function of this reference spinner. Because it's a reference, it can be chosen arbitrarily. And the way to check it is you can show that the difference between any two arbitrary choices of this C is always proportional to the momentum. So this is the most fundamental requirement of these polarization vectors. So, so because this change is proportional to P, it's basically it's a gauge transformation. So if you consider any contractions of these amputated Feynman diagrams with these external polarization vectors, if it's proportional to P, basically the physical degree of them has to be perpendicular to the momentum. So if it's proportional to P, this is has to be 0. So that's a basic physical requirement. So that's also a different way to say that it's a gauge invariance transformation. So I should also mention here, there are actually so in the real Minkowski, because the momentum have to be real, so this lambda tilde should be plus minus this conjugate. So the plus minus depends whether the energy component of momentum is positive or negative. However, there's no constraint for the choice of the complex Minkowski. So in this case, lambda and lambda tilde are independent. So this is a very important concept that will allow us to introduce if you use a spin analysis formalism. So as for example, without introducing these complex momentums, it's impossible to define a non-zero three-point amplitude, which is it's a very simple fact, but it's really powerful. I should make a comment here. Okay, so that's basically some basic setups of notation. Now this will be the many other speakers will probably rely on this fact. And as the last point of this spin analysis formalism, I would like to tell you what's the basis of this spin analysis formalism. So in terms of this, so any Lorentz invariant of this function will be a function of this spinning contractions, ij, the square brackets, or angle brackets or square brackets. So we see that from the Euro 4 vector contraction to this spinning contraction is quite nonlinear. Okay. So because there's many relations between these spinner variables, you can have two different expressions which